Hello everyone, my name is Josh and welcome to today's video. In today's video I'm going to talk about logarithms. I'm writing in my joined up handwriting, so please just pretend that you can read it. So a logarithm is an interesting function that is classed as the opposite to an exponent. So basically what this means is if you've got a power, say 10 to the 3, so 1,000, and you take a log to the base 10 of it. So a logarithm is an inverse to an exponent. So an exponent being like a number x to a power n, like that. So here we've got an exponent of 10 to the 3. So if we take a log to the base 10 of that, what we will get back out is the 3. So it's basically saying for a log to the base a of a number b is how many orders of magnitude of a is there in b. So this is very confusing and difficult to explain to someone. So a good way to think about logs is you've got the base of a log here in this a. So what power of a gives the number b? So in this case, where we've got log to the base 10 of 1,000, it's what power of 10 gives this number inside 1,000, and that would be 3, because 10 times 10 times 10 is 1,000, so it's just 3 in this case. So you can take a log to any base that you like, and the same principle just applies. So you can have log to the base 2 of 8. Now, in 8, you can get it from 2 times 2 times 2, which is 2 cubed. So that means log to the base 2 of 8 would give you the 3 from the top. Let's just draw that circle around a bit neater. So that would be equal to 3 as well. So there are special cases of logs. You can take a log to any base that you want, but there's a special one when you take it to the base e. Now, e is a number in maths which is about 2.713 or something like that, which is just a special irrational number quite similar to pi. Now, if you take a log to the base e, it's called the natural log, ln. I don't know why it's called this. It's rather peculiar, but if you see ln written down instead of log to the base of something, it's just the same as writing log to the base e. Now, you can use logs for many different things when it comes to solving equations. So there are some special rules that apply with logs. So I'll write them down on this side of the page. So we have a power rule of log, a power rule. We have a multiplication rule of logs. So if we have the log of a times b, we can separate that out into the log of a plus the log of b. Which doesn't seem all that useful until you start talking about it where you don't know the value of either a or b, at which point you can start using it to solve equations. So we have that one. Similarly, we have log of a divided by b is equal to log of a minus log of b. Excuse my terrible handwriting anyway, but if you are struggling to read anything I've written down, then just mention it to me in a comment and I will write out what it should say. So this is another similar rule, which again is useful when it comes to solving. Another rule is the log of a to the power b In each of these cases, a and b are just two numbers or two unknowns, whatever it is that you're solving for. So log of a to the power b is equal to b times log of a. Now, again, this is just something you can use to simplify equations down. And so another rule with logarithms is the root rule. So if you have log of a to the bth root, which is awkward to say, that is equal to log of a, log of a over b. It's just you can see it's the opposite of taking to the power. You just divide by instead of multiply by. And there's one other special rule where you can do a change of base. So if you've got a log to the base c of a, divide that by a log to the base c of b, that is equal to a log to the base b of a. It's another strange rule that is just useful to know. So these are your logarithmic rules. They are very useful to know and often come up in exam situations of just simplify questions or solving an equation for x if one of these numbers, a or b, is unknown in a complicated series of logs. It's useful just to do that. So a couple of interesting logs to know about. There is log of 1. It doesn't matter what your base is. If you have a log of 1, that is always equal to 0. And so this rule comes about through the graph of a logarithmic function. So a graph of a logarithm will always be asymptotic to the y-axis there, and then take this, be asymptotic to the y-axis and take this sort of curved shape. This is supposed to be a smooth curve, but I just can't draw them very well. Or this shape, the size of this always depends on what your base is. But they will always cross through the same point, and that point will be 1. So at log of 1, where x is 1, the value will always be 0, because whatever logarithm you plot, it always crosses through the point 1, 0. If you end up with a log of 0, then you have done something wrong. Log of 0 is impossible. No logarithmic function ever crosses through 0 on their graph. And so if you type that into your calculator, again, whatever base you use, you will end up with a math error because it's not possible to calculate. So remembering logs are just the counter of exponentials. So an exponential will look like this sort of shape. That's an exponential growth in x, so like e to the x, for example. And that will cross through 1 there. So you can see how these graphs are just inverses of each other as they are opposite operations. And that's useful to know for if you're asked for a graph, or even just for your own benefit to know kind of what the functions look like. So I will take you through some example questions now. So the first one we'll take log to the base 7 of 7. Now log to the base 7 of 7, so 7 to what power makes 7? And that would be 1. So that sum would equal to 1. That looks like 1 over 2. So that sum would equal to 1. If you get something of the form log to the base, I don't know, let's say 5, log to the base 5 of 1. Remembering this rule from before, log to the base 1 of anything equals to 0, because in this case 5 to the 0 equals 1, as anything to the power of 0 always gives 1. And in this case it's 7 to the 1 equals 7. So it's always just the power on these bases. So another one we'll take, we'll say log to the base 3 of 2 plus log to the base 3 of 5. Now this one is equal, using one of the previous rules, to log to the base 3 of 10. And that's just because log to the base a of x plus log to the base a of y equals log to the base a of x, y. Just using that rule from before, so this one comes out to log to the base 3 of 10. Now, 3 doesn't have a power that makes 10 exactly, that's easy to calculate in your head. So whatever this one is will come out as some decimal number, which you can work out if you just put this in on your calculator. It's log to the base 3 of 10. If we pick another one, so we'll say log to the base 6 of 54 minus log to the base 6 of 9. That equals log to the base 6 of 54 over 9. And that is equal to log to the base 6 of 6. Just cancelling this down. And that is equal to 1. This time we're just using the negative version of this rule, equals x over y. Another one we'll do as the final one. We'll do log to the base 2 of 5 cubed. That is equal to 3 log to the base 2 of 5. Just using our power rule, so we take the power in front. So those are some very simple log rules. So this time we'll go through a bit more of a complicated simplification. So this is more the style of one that would come up if you sat an exam with this subject in it. So we'll say 5 log to the base 8 of 2 plus log to the base 8 of 4, forgot to put brackets here, minus log to the base 8 of 16. So in order to solve this one, we've just got to remember our rules. So we'll do, we'll simplify this back to its original form, what it would have been. So that would be log to the base 8 of 2 to the 5, remembering our power law, plus log to the base 8 of 4 minus log to the base 8 of 16. So then we will simplify this bit together using our addition law. So that's log to the base 8 of 2 to the 5 times 4 minus log to the base 8 of 16. So then simplifying again, we get log to the base 8 of 2 to the 5 times 4 over 16, this time using our subtraction law. So that's where we're at now. So we can solve this. This is equal to log to the base 8 of 32 times 4 over 16. and that is all equal to log to the base 8 of 8, and log to the base 8 of 8, so 8 to the what equals 8, well that would be equal to 1, so this whole thing just cancels down to 1. And that's the power of solving with logs. We can go from an equation in this complicated format just to a single number, all of that equal to 1. And it makes it very useful for solving equations with this kind of thing. It's also likely that you could get a question to work out what the value of an unknown is when they give you an equation in logs. So we'll do an example going through this. So this time we're going to go through a question where we have an unknown in it and we want to solve for a value of x. So the equation we're going to try and solve is natural log of 10 minus natural log of 7 minus x equals natural log of x. Now, you may look at this equation and just be like, well, what am I meant to do with that? I've just got a bunch of logs with a couple of unknowns on each side. It makes it kind of confusing to solve. So, what we'll do, when in doubt with logs, just use the rules you remember to simplify the equation as much as you can. So, we'll start off, we've got this subtraction here, so we'll do the natural log of 10 over 7 minus x, grouping those up together, equals natural log of x. Now, in order to get rid of a log, you remember I told you that the exponent is the inverse of a log and vice versa. So if we take an exponential of both sides, so it's e to the power of all of that, e to the power of that, the exponential will cancel out with the logarithm each time because they're the opposite of each other, and all we'll be left with is 10 over 7 minus x equals x. Now this is a complicated step, but it's good to get your head around. So if you take an exponential of a natural log of something, you will just be left with whatever was inside the natural log, because these two operations will always cancel out. And the same goes for if you've got any log, so log to the base 2 of 5. Well, in order to cancel that out, you do 2 to the power of the log. So if you just do whatever the base is to the power of a log in that base, it will just leave you with whatever was in its bracket. So that means here we've now got this. So this is more looking like an equation that we can solve. So we rearrange this to put our x's on the same side. So we say 10 equals x times 7 minus x. Expand that out. So 10 equals 7x minus x squared. And now we'll rearrange this to get x squared minus 7x plus 10 equals 0. So we need to make minus 7x and 10, so the factors we can use is x squared minus 2x minus 5x plus 10 equals 0. If you're unfamiliar with how I'm factorizing this, then just have a look at my other video, my first one, called Solving Quadratic Equations, and that will show you the methods I'm using right now. So then we'll factorize this, so we have x minus 2 minus 5x minus 2 equals 0. So then we'll go back up here and we say x minus 2 x minus 5 is equal to 0. And so that means that we get solutions for x of x equals 2 and x equals 5. And that's how we solve equations when we have unknowns in x with logarithms. There are lots and lots of examples you can try online. If you get particularly stuck with any and don't understand the solution, feel free to comment them or message me about them and I'll try and help you understand. I've tried to keep this video fairly brief, but it is quite a complicated topic. But if you just work through each question with the rules that I've shown you, especially when you're solving them, this one, you should be able to handle any log question that they're likely to throw at you in an exam, because they'll most likely either get you to simplify a set of known logarithms down like this, using the rules that we showed in the first slide, or they will get you to solve an unknown in X, like I've just shown you on this side. So it's all just about knowing how to cancel them out and rearrange. I hope this video has helped with your understanding of logs. I understand that I've kept this one a bit brief because of time. But if you have any more questions to do with logs or get stuck on a particular example, as I've said, just let me know. I hope this has helped. Thank you for watching. If there's any more topics people think of watching this that they want me to go through, if they want me to make a more detailed video on this one, then just let me know, as always. So thank you again for watching, and I hope to see you next time.